Hello everyone, welcome to the numerical methods class. In this class we are going to talk about the numerical differentiation. If you remember, we actually talked about this while we are teaching the Taylor series expansion. But now in chapter 23 we will go into deeper meaning of this and show further numerical methods that we can use for differentiation. If you remember, in chapter 4 we used Taylor series to be able to get numerical differentiation using the finite divided difference approximation of derivatives. And you can see here a Taylor series. And in this Taylor series we were isolating f prime, which is the first derivative. And then we were able to get fxi plus 1 minus fxi, and also minus this and the rest you can see on the right hand side. And this gives us the first order finite divided difference approximation for the first derivative when we truncate after this term. So we have an error of OH if we truncate after this term. If we truncate after this term, then OH square, of course. But here this is the first derivative, the simplest version of the finite divided difference approach. It's just the xi plus 1 function value minus fxi function value divided by the step size between these xi plus 1 and xi. And for the second derivative, simply we isolate from here the second derivative. Then we are getting, for example, this function, which three terms. In the first derivative, we need two known function values of two x values. In the second derivative approximation, we need three function values and three terms. When we substitute this f second derivative finite divided difference value or function into here in second derivative value, then we will be able to get this value here as well as this one here. And you can see we have now two finite divided difference approximations in one estimation of the first derivative. In this scenario, when we organize this, we will have a finite divided difference approximation with three terms for the first derivative, and now our error is in the second order. In this one, when we isolated only the first derivative, our error was in the first order. When we kept the second derivative and substitute the numerical approximation for the second derivative into here, we obtained a second order error. So we were able to get a better approximation for the first derivative. Of course, for this you need three x values and three function values of these x values, which is different from the first order approximation, which has two values. Including the second order term for the second derivative, this one, improved the accuracy of f prime xi to OH square. So we have OH square because we added the second term as well. So we improved the error, or the accuracy actually. So this is called the high accuracy numerical differentiation. We simply improved the derivative estimation by adding the next derivative approximation into the first derivative formulation. And similar improved versions can be developed for the backward and centered formulas as well as for the approximations of higher derivatives. We can show these in the next slide. When we use the same idea that we used in the previous slide to be able to get higher order accuracy or a higher order finite divided formulas, for the first derivative, this was the simple formula that we learned in chapter 4, and this is now the improved formula by adding the second derivative finite divided approximation into the first derivative after truncating from the second derivative. So we have an order of h2 with this formula for the first derivative. We can do the same for second derivative. This is the first simple formula for simple approximation, and this one is when we add the third derivative approximation into the second derivative after truncating from the third derivative, for instance. So this is the formula for the second derivative with higher accuracy. For the third derivative, similarly, we will have a higher accuracy formulation over here. So you can see that we will have additional data, one more data compared to the simple one, but it will increase the accuracy very well. And the fourth derivative is here. For the forward finite divided difference formulas, finite divided difference, we can use these improved versions to be able to get better derivative approximations. Let's move on to the next slide to see the backward finite divided difference. We can do the same idea for the backward finite divided difference formulas. For the first derivative, this is the simple version, and this is the more accurate version with H2 error magnitude. So for second derivative, you can see here again an improved version with H2, and for the third derivative again with H2, the more advanced one. This is the simple one, simple version. And also for fourth derivative, you can see that we have an improved version as well. Because this is a backward finite divide difference, we have I-1, I-2, I-3, I-4. So we have the backward values or terms. Let's move on to the next slide to see the centered finite divide difference. Remember from the chapter 4 that the centered finite divided difference had better accuracy compared to the forward and backward finite divided difference. And now we are using it to be able to improve the accuracy further by adding an additional term so that we can get a higher accuracy for the finite divide difference approximation. This is for the first derivative, and you can see that it was xi plus 1 minus xi minus 1 divided by 2h for the first derivative simple version. For the accurate version, we have I plus 2, I plus 1, I minus 1, I minus 2, and 12h. For the second derivative, we have this simple version and this more accurate version with h2. For the third derivative, again, we have this, and the advanced version is this. For the fourth derivative, we have this, and for the simple version, and for the fourth derivative, we have this as the improved version. You can see that we have further terms, and because it's a centered finite divide difference, it's centered, the xi is centered, and the other terms are increasing and decreasing, like symmetrically, I plus 1, I minus 1, I plus 2, I minus 2, and I plus 3, I minus 3. That's why it's called the centered finite divide difference. So you can use all of these derivative formulas to be able to estimate the derivative with a higher accuracy. We have an example here, and in example 4.4 we used the derivative formulations we obtained from the Taylor series to be able to solve this equation, and the true value for the 0.5 derivative, or for the x equals 0.5, is minus 0.9, 125, and we want to see if we can get similar results with this by using the higher accuracy first order formulas, and we will use h equals 0.25. So for the forward finite divided difference, we have these formulations. This is the simple version and this is the accurate version. Let's use them. To be able to use these, xi plus 1 and xi we need. So xi is actually x equals 0.5. For forward, we need xi plus 1. So if h is 0.25, we need 0.75. Then when we calculate it in this function, its value is this. So when we use these two, 0.5, 0.75, and these, the result is this one, h is 0.25. Now for the more accurate one, we need xi plus 2 as well. That means we will add one more step size to this, and the term is 1. So calculate the function value for it and use it in here, and the result is this value. When we compare these with the true value over here, this is in the magnitude of h, and the error is 26.5. You can see there is a difference. And for the second one, the error is actually reduced, like quartered, because the order is in the second order now. So it's about 5%, 6% difference. Let's use backward finite divide difference formulations. In this case, because we have xi here, and we will have xi minus 1 and xi minus 2, so we will subtract the h value from this to get I minus 1 and I minus 2. So these are the values, 0.25 and 0, of course, when you subtract from this. And these are the function values from here. Let's use them in here. When you use only I minus 1, this value, the result is this. When you use this one as well, the result is this. So let's calculate the errors. Here 21.7% for the simple version. For the more accurate version, it's like 4%. It's very accurate, you can see. Let's check this centered finite divide difference. In this we will use not xi, but xi plus 1 and xi minus 1 in here, and also xi plus 2 and xi minus 2 in here. When we use them, the results are much closer to the true value, because we know that the centered finite divide difference is a better approximation compared to these ones, because it's using actually additional data in the formulation. Here the error is 2.4 and here the error is 0, and with this actually we can get the exact result easily for this formulation. So centered finite divide difference is preferred if possible, if we have this enough data to be able to calculate this approximation result.